Our first talk for the afternoon will be by Shantanu Basu, who will tell us about fragmentation of clouds to cores and disks.
Okay, thank you, Chris. Thank you. It's a pleasure to be here. Thanks for all who organized. And I must say it's quite an honor to be speaking at a meeting in honor of two very eminent astronomers associated with magnetic fields. And I'm not part of the immediate family of either Dick or Carl, but I feel like I'm part of the extended family because I worked with Telemachus Muscovius, who was one of the preeminent theoretical people on the magnetic field side. And so, you know, we've had a lot of interaction, more with Dick because we were all at Illinois. And I'll mention a couple of things about that as we go along. So I wanted to start with just the kind of the laundry list of some, probably not all, the topics that we're all interested in as B-level scientists. And that's okay, because B is a vector. And I'm sure many of these topics have been covered already, and I'm not certainly going to cover even many of them, but the ones highlighted are ones I'm at least going to try and touch on, and then set ourselves up, perhaps for future talks in this session. So the first point there about magnetic field support, now that gets me back to my comments about Telemachus and then to Carl and Dick. So a bit of a historical trip down memory lane, or for the students here. You know, it was Telemachus who in the 1970s really started advocating this idea that magnetic fields could be the explanation for the observed low efficiency of star formation. And so the idea was, wouldn't it be nice if there was a reason other than outflows and feedback, perhaps, which could explain low efficiency, and you wouldn't rely on the stars themselves to create the reason for their inefficiency. So you could have a reason that extended to low mass star forming regions where you may not have a high mass star around that could disrupt everything. And so Telemachus had this very influential series of papers, especially this 1976 paper, whoops. And let's go back. So this figure, of course, is from the days of the draftsman, where you put all the information on one plot. So I'm not even going to try to explain everything, but you can certainly see these are density contours of an equilibrium cloud. And here's the hourglass magnetic field lines that are part of the self-consistent equilibrium. So this is a very nice method of self-consistent fields. Never mind the dashed lines, they're equal magnetic field strength contours, and those are less intuitive. So Telemachus really had this precursor idea of magnetic support, and I think it's very nice to go back and see what he wrote. And certainly he's addressing head-on this observed inefficiency of star formation. That's what makes magnetic fields really interesting from this point of view. They'd be less interesting if they were just a passive spectator in star formation. However, you need a way then for it not to always be so strong, and so then you expel the magnetic field, or really mass-to-flux ratio, from the cloud core at high enough densities, and therefore you somehow, you know, you can get to your star forming and even having a weak field in the star when you form it. Okay. In this paper, so I'd urge you all to read about that, and that's led to subsequent work on the density, on the PDFs of magnetic fields, and perhaps more. But what I want to emphasize here is that they pointed out that, okay, if you look at the H1, you can think of the cold neutral medium sheets as perhaps being these transient structures brought together by large-scale turbulent flows, and they would perhaps increase in density because of turbulence, but then eventually limited by magnetic pressure. And then they contrasted to what might be another view, at least for molecular clouds, which was more of a static view of static equilibriums. This is going back to literally the Muscovius model on the previous slide, where you have equilibrium states, and then you slowly, maybe at least in the interior, you evolve through ambipolar diffusion. But then they made an interesting point that actually both ways of looking at it might essentially lead you to expect equipartition of energies. And unfortunately, we can't seem to get away from that. Many models of different assumptions do ultimately give us equipartition, and observations often are giving us equipartition. So they were trying to say, well, is there a way you can disentangle that? And I'm going to try and convince you that you can, and that basically, so the point of view I'm presenting today is that you can actually think of this turbulent flow picture in the molecular cloud, and yes, you'll have equipartition, and you'll still preserve some elements of this, this view, or the one on the previous slide, where you actually maintain magnetic support on the large scale. Now, the H1 gas with the Zeeman, we've seen this many times before in many forms. Most of the data points of line of sight and magnetic field against column density place the H1 gas in the subcritical regime. Okay, so on average, it's subcritical, few outliers. And then if you combine that with the molecular data, again, we've seen this lots of times, so I'm not going to spend much time on this. And you see this transition at some critical density. You know, one simple interpretation then is you're building up the molecular cloud from subcritical components, primarily by motions along the magnetic field. Then, you get to self-gravity. Now you have to include the effect of gravity, and then you're evolving up this line through at least approximate flux freezing and approximate criticality, critical mass-to-flux ratio, at least for the upper envelope. Okay, and so then again, you've had some discussion of what the slope is. In this fit, it's 0.65 in this region. My point here is that we shouldn't really spend too much time worrying about whether that is different by 1 decimal place, either the first or second. But I'll point out that there is this paper by Tristis et al. Who, whoops, so let's go back, yeah. That's really the one I want to get to, but okay, let's stop here. Who point out that, of course, there's error bars in this direction as well. And if you look at the various density estimates, you're going to get a different fit, perhaps, taking into account both bars. And then they look at only the molecular, not combining it with a model for both atomic and molecular. And there's some discussion as to what your starting point is and how that affects your slope. So they get somewhat different slopes based on taking either the upper limit of densities, or this line is from the lower limit, LL. So now you're coming back to 0.5 or so. But anyway, my point is not that it is 0.46 or 0.5, but that we're really limited in our data, right? We're still dealing with small number statistics. And there's many ways to skin this cat. And you're going to get slightly different numbers depending on how you do the analysis. And in fact, I pointed out about 15 years ago that B versus N isn't necessarily the complete correlation you should be looking for. If you take into account the velocity dispersion, you actually get a much tighter fit. Again, this would be for the upper envelope, the confirmed detections in Zeeman as of 1999. But it was a much better fit, and essentially that's a virial relation. This is telling you that your magnetic and turbulent energies are comparable. And it also turns out from molecular clouds that those are both comparable to the gravitational energy, because you have a roughly critical mass-to-flux ratio. So the actual absolute position of this line, the fact that it's not here or there, gives you the last correlation. Okay, so I think given all of this, I don't think it's very fruitful to worry too much about what the exact exponent is if you take B versus N. But now all the rage is filaments in molecular clouds, and if you go back to Taurus, so this has been well known for some time, but most recently measured by Palmerim, this filament B211-213 has the magnetic field in projection going perpendicular to the length of the spine. So hence implying if the field is important, it's probably not a cylinder, a perfectly cylindrical object. If the magnetic field is going this way and has some dynamical importance, it would certainly distort you from that shape. Now, one nice scenario in which you would naturally get filaments as well as magnetic fields that are pointing perpendicular to the filament is a scenario of turbulence, magnetic fields, and gravity all being comparable, but actually having the magnetic field be at least somewhat dominant in the low density regions of the molecular cloud, perhaps consistent with it having accumulated by H1 clouds, but not having accumulated as much matter as other regions. And so when you get near critical, though, so this wouldn't be highly subcritical, it could be within a factor of 2 of criticality, then your turbulent flows will naturally give you these elongated structures within which you can get rapid ambipolar diffusion, star formation, and in this direction, you've got settling along the magnetic field lines. So this has been, this picture, Nakamura-san has developed very strongly in the mid-2000s, along with Zia and Lee. Bruce Elmagreen wrote a nice paper talking about this, and various papers have been published. And I think that's a theory, but here's observation that at least has some elements of that in it. So this is, again, B211, 213 in there somewhere. Anyway, it's Taurus. And you've all seen this before. It's however Planck makes this magnetic field representation. And you certainly see by eye that the densest regions seem to have the field going through perpendicularly, but then the lower density regions, it's more complicated. And maybe this is consistent with the idea with the BN plot where your B is more or less not changing much because it flows along the field line, but eventually you're getting into the self-gravitating state where B and N will be correlated. And here's a histogram, essentially the probability function of the offset between the magnetic field and the local column density for 3 different column density ranges, the red one being the highest column density range, the black one being the lowest. So let's just focus on those 2. So black being between 10 to the 20 and 10 to the 21 per square centimeter. And this histogram is actually peaked at around 0, which means the field is more parallel to the field than perpendicular. And the red line, which is the highest column density, is peaked more at minus 90. So it's perpendicular to the magnetic field. Okay, so back to those models of accelerated turbulent ambipolar diffusion. Let me show you an animation of a 3D simulation of an initially subcritical cloud when you add alphanic turbulence. And since it's, let's see, oops, missed it. Let's go back. Yeah, okay, right. No, let's go back. Find the cursor. Okay, got it. Okay. So this is your subcritical cloud with turbulence. It's actually going to be oscillating. It's dynamical oscillations, because flux freezing alone will not allow any region to collapse in a subcritical cloud. But because you have ambipolar diffusion, this is 3D. So this is the 2D face-on view, and this is the side-on view. Okay? And so eventually you get some regions that do run away. So this region is collapsing. It's in some larger elongated structure. Of course, it's not a straight filament. It's curved. But you basically have this picture of filamentary structures in which you have runaway collapse in local pockets, okay? And so this was a case where the turbulence is transalphanic, and here's the time dependence of the density. It runs away within a couple million years, whereas if you had linear perturbations, it would take about 10 times longer. So now what we did in a more recent paper is we simplified this model to understand the essence of it. So if you have a filament and it's going to collapse, can we analytically understand the rate at which that's going to happen? So you can reduce 3D to 2D now, but 2D is not thin sheet. The 2D is vertical and one of the 2 dimensions perpendicular to the magnetic field. And you put in a sinusoidal perturbation and you watch the filament form and oscillate. So it's the same physics as before, but with one less dimension. So your filament really is straight now, and it's oscillating back and forth, and you can see the views from 2 different sides. And it's going to undergo these dynamical oscillations, but there is ambipolar diffusion active, so eventually it's going to collapse. Okay, so now you've got star formation going on. And when you model it this way, you can do it numerically like that, or you can actually analytically get to the heart of it. You can say, well, your filament, when you form it, essentially balance between magnetic pressure on the inside versus turbulent pressure and the external magnetic pressure. Those come into balance, And that's what causes the oscillations. And you can rewrite that this way. And then you rewrite it again. And you can write down, you can calculate the ambipolar diffusion time given the equilibrium density that was on the previous slide. And it turns out to have this more complicated form than the traditional static ambipolar diffusion time that we were using decades ago. This now includes the Alfvén speed and the turbulent amplitude. That ratio is very important. But if you're looking at trans-Alfvénic turbulence, where that's 1, then you've essentially got the old ambipolar diffusion time. Well, that's related to the collision rate of neutrals with ions. You've got the traditional one with the 1/3. Okay? So it's very nice. You can actually come up analytically with the fact that with the turbulent flow, you get 1/3 the static ambipolar diffusion time. Okay, so you can also write that in terms of free fall time and neutral ion collision time. Sorry, that should be an approximately equal to. Okay, you never know with these projectors. Okay, and that's the Alfvénic limit. But you could also be super Alfvénic to test your theory. So if this was highly super Alfvénic, then this number essentially scales as 1 over the turbulent amplitude squared. And so this is a series of simulations with different mass-to-flux ratios. And when you're trans-Alfvénic, like here, you have a pretty good fit to the time scale to form a runaway core in the simulation. And then as you go more super Alfvénic, you definitely follow this 1 over turbulent amplitude squared relation. Okay? But I'm going to focus on the fact that you're probably looking at the Alfvénic limit. That's where we are observationally, if you look at the numbers. Okay, so that's one application of this semi-analytic model for filament formation in this dynamical oscillation scenario. Another application would be to look at the widths of these filaments. And before I show you that, I'll show you this observational plot that at least in some other conferences I go to now, this is put up all the time, which is the full width half max of the filaments detected by Herschel in low mass star forming regions versus the central column density. And it's roughly a flat correlation over 2 orders of magnitude column density. And so the big question here is, why doesn't this look like the Jeans length? We should be doing this. If you believe that these are perfectly isothermal equilibrium cylinders, then the flat central region is essentially that. That's what you would expect. So it's not doing that. Maybe you're measuring it in some crazy way, but however it is, it's not doing this. We're doing more like that. And in our filament model, we realized that, well, ribbon really, that we're certainly not looking at a cylinder, but we are looking at an elongated object. And it's elongated in the following sense. You've got magnetic field going this way, and along the magnetic field, your thickness will be essentially the Jeans length. But perpendicular to the magnetic field, your thickness is set by that interaction between magnetic fields and turbulence. It's like the quote from Carl and Dick's paper about turbulence compressing gas until it comes into pressure equilibrium. But that standoff length would have nothing to do with the Jeans length. That's completely different physics. And you can derive an expression for that length, again, in terms of this ratio of turbulent amplitude to Alfvén speed. But it depends also on what the initial wavelength is from which you're drawing material. Again, it'll be essentially, this will become 3, so it's 1/3 of the initial wavelength. We don't know exactly what that, there's no first principles theory as to what it has to be, but essentially if you look at the actual maps of filaments or the time scale argument that you need to correlate star formation over a couple million years across a filament, it basically has to be about a parsec. That's basically the initial scale over which you're drawing matter together. So this final length scale might be a third of a parsec. So if we look at synthetic map of observed width versus observed column density using our ribbon model, and one dimension is essentially Jeans length and the other dimension is some fixed scale, then over the various observing angles that you would view this object, so we're taking random angles between 0 and 90, so these are synthetic data points, and the black line is the average of the data points of the various column densities, it's roughly flat. It's not exactly flat, but it's nowhere near steep as the Jeans length. Okay, so it's an indirect, there's indirect information here in certainly the Arzamanian observational map that it's not the Jeans length, it's not an equilibrium hydrostatic hydrodynamic cylinder, it's something else. And this magnetic ribbon model is at least giving us something similar because the physics is not just the Jeans length. Okay, so next topic I want to cover is the hourglass magnetic field. Of course, we've learned today that it's far more complicated from ALMA, but at least on certain scales, prestellar cores and early protostellar collapse on large scales, the hourglass could be prevalent, or it could be valid in at least some regions. And of course, we've known about hourglasses since at least Schleuning's map of OMC1. And this is a Bach globule, B68. I'm not sure this is even published yet, but I got the image from Kandori-san. And of course, this is the famous RS4A. And these are three very different scales. That's what I wanted to point out. Okay, so you can get them at many scales for many different reasons. From a theoretical point of view, you can get them whether you have turbulence or you have pure gravitational contraction. In a kind of quiescent gravitational contraction model, you'd get something like an axisymmetric hourglass. Whereas in a turbulent model where you're creating elongated structures, you get an hourglass, but it's not axisymmetric, right? It's along the spine of this filament. And again, we tried some analytic fitting to our simulations, and we found that we got a good match with the following. So the red lines are an hourglass in one of the simulations of core formation, one of the 3D simulations. And the blue lines on top is an analytic model, which is essentially an exact solution of Maxwell's equations if you're assuming your electric current is confined near the midplane here. And your solution is an infinite series involving some of your favorite special functions. Not really so scary. You can code this up in no time. And what you get is essentially some kind of Bessel function in the vertical component of the magnetic field. And the radial component is peaked and then declines. So you can see the peak curvature there. The advantage of having an analytic form then is you can do fitting relatively simply, and you can adjust the parameters. So you can adjust your parameters, and for example, you can actually use it to measure the ratio of central magnetic field strength to the asymptotic field strength. You've got just three parameters, essentially: the vertical thickness of your current sheet, your radial extent, and that central magnetic field. So that's a simple-minded hourglass, and it's nice. It's a simple Maxwell's equation solution under minimum assumptions. And then a more complete and different way study was done by Kataoka et al. This is a very nice work where they took simulated hourglass fields, including the protostellar phase, and including misaligned cases where the magnetic field and rotation axis are not aligned. And they looked at synthetic polarization maps, and the interesting result was when you look at a case where the rotation axis is misaligned with the magnetic field, and you've got significant rotation in the inner regions, you're generating some toroidal wrapped field, then you can actually get either an hourglass. If you're, say, viewing from this side, you'd get an hourglass pattern, classical. But if you're viewing from 90 degrees the other direction, you get this S shape. Okay, so you can follow that. Okay, so that's a very nice result. And their claim is that also the S shape becomes more apparent over time. So you have some hope in pinning down the evolutionary stage and the viewing angle based on the shape of the S. Okay, again, but starting with a particular model. So I think there's a lot of scope here for doing some kind of model synthetic field mapping, at least for hourglasses. Now, the stuff we saw from ALMA today is far more complicated, and we're having a nice conversation over lunch today. That that will take yet another leap of imagination. But I think the basic idea of taking analytic or semi-analytic models and doing synthetic polarization maps, now that we have all this data, should become a kind of cottage industry for some of you. So now I'll talk last about disk formation. It's been claimed that magnetic fields can prevent disk formation. And yes, that's true in the ideal MHD limit, because you at least for an aligned rotator in ideal MHD, because you're linking small radii with very large radii, a huge lever arm difference that exerts too large a torque to create a disk. But typically the simulations that claim that there's a magnetic braking catastrophe would typically have ideal MHD, and they'd have a central sink cell, which would be 7 AU or so. And so you're really not saying there's no disk, you're saying there's no disk larger than 7 AU in that case, or whatever the sink is. So in our modeling that we did a few years ago, we put the microscope onto the inner region and included the microphysics of non-ideal MHD. And I think that's very important to get the whole story. And so bottom line, yes, a disk can form, right? You've probably heard that already. But they would be small, because you would lose a lot of angular momentum on the way in. So I'll just show you a few slides on that, and I think I'm almost out of time, so I won't spend a lot of time on this. So if you want to do the non-ideal MHD correctly at the high densities, you have to do chemistry or some approximation to chemistry. And so we had a model for the ionization fraction and hence the resistive coefficient that included all of these different effects. So normally, low densities, you're just interested in electron-ion recombination, balancing your cosmic ray flux. But then eventually, grains become important and start mopping up grains, and that leads to a halt in the decrease of ionization fraction. However, it doesn't lead to a halt in, well, I'll get to resistivity later. And then eventually, your cosmic rays get shielded out. You just have residual ionization due to radioactive decay. And then above 1,000 degrees Kelvin, you get ionization back through thermal effects. And you can convert that into a diffusion coefficient, which essentially is rising, rising, rising. Even when the grains are absorbing charges, you may have more charge carriers around than you otherwise would, but the grains are awful at sticking to magnetic field lines because of their low cyclotron frequency. So the resistivity goes up again, and it keeps going up until you get the thermal ionization, and then you indeed go back toward flux freezing. So one of the bottom lines of this study is, to connect to the hourglass, if you look at the late stage of the evolution, you have a second stellar core sitting right there and right here. So this is the first one to look at. If you look at this map, this is essentially an 80 AU box. The red lines are what the field lines would be if you had ideal MHD. The blue lines are the more relaxed version when you have magnetic diffusion. And you can see the field lines have pulled back. In the absence of resistivity, you have a split monopole magnetic field. Yes, it actually is radial if you have ideal MHD. But the more realistic case is drawn out. But you can see out at 60, 70 AU, there's not a whole lot of difference between the field lines. But if you zoom in on the inner 10 AU, there's a dramatic difference. And this is the reason why you're not getting, you are getting catastrophic magnetic braking if you have the dashed red lines, but not if you have the blue lines. You don't have as big of a lever arm difference between the disk surface and the far magnetic field. So this was our result, that you would get the disk, and I'm not presenting numbers on the slide, except that the amount of angular momentum we have when we form the second core is consistent with forming something like a 10 AU disk in the first few times 10,000 years. So, I mean, of course, you could have more angular momentum in your system and all that. So these numbers are not absolute, but roughly you're talking about disks of the order of 10 AU in the first 10,000 years of life of this object. So that's a testable prediction. So class 0 objects, there's an argument. Some surveys have found small disks or lack of evidence for disks below 50 AU. There's a couple of class 0 objects where there does seem to be evidence of large disks, although it's not clear what the age is in those cases. So my point is, with non-ideal MHD, you can get a disk. You can get a moderate disk, not a big disk. But of course, even a 10 AU disk would grow over time and become a 100 AU disk due to internal angular momentum transport. But if you need a large disk in 10,000 years, then you have to appeal to these other effects, the most prominent of which is misalignment. Again, if you misalign the rotation and magnetic axes, you don't get as big a lever arm difference between the inner region and the outer region. And that lessens the effect of magnetic braking. And these authors showed that you can actually get a disk to form under some of those circumstances. And then there's the various ways that turbulence, reconnection, and warping, these are all related, really, can give you some kind of complicated, tangled structure that would either reduce the effectiveness of magnetic braking or reduce the magnetic flux itself, ultimately through reconnection. And so those are other ways where you may be able to break the effect of the magnetic field on larger scales than you could with the classic resistivity alone. Okay, so that's all I wanted to say about that, and I'll just conclude with my summary slide. Okay, thank you.
Thank you, Shantanu. Questions?
You show that ambipolar diffusion and collapse can be enhanced by turbulence. But is there turbulence support against gravity also taken into account? And is there a lower limit of the ambipolar diffusion timescale for this reason?
So if you're asking whether there's turbulence on even smaller scales, well, what we have is a power spectrum of turbulence, okay? And so most of the power is on the largest scale. And so therefore, in many ways, it looks like a large-scale flow that's bringing your filament together and creating it. There's not necessarily a lot, although there is some, of internal pressure support within the filament. I mean, I would say it would not make a big difference if it was subaphanic, which it is in this case. But you need a very large internal turbulence to affect the thickness of that filament.
But ambipolar diffusion also operates over large scales.
That's right. That's right. Yeah, it does. It operates essentially on every scale. So if you have some kind of gravitating center, if you have a self-gravitating cloud, you'll have ambipolar diffusion going on all scales because the neutrals will be moving under the influence of gravity, and the ions will not be able to keep up at the same rate that the neutrals are moving. It may not be a huge effect, but yes, I agree with you. I don't know if that's what your point is, but there is ambipolar diffusion on every scale. But if you compress a layer like this into a sharp filament, now you've got high density and a strong magnetic field gradient locally. So in that local region, ambipolar diffusion will operate rapidly, more rapidly than is happening on the large scale. The large scale ambipolar diffusion you can think of as more like the static ambipolar diffusion that I mentioned at the beginning.
Okay, Alex?
Definitely, ambipolar diffusion is an important effect, and no one questions its validity of this concept. But I think by now we also have proven that there is no perfect flux conservation in ideal fluid if the presence of turbulence. And I think this should be taken into account. Also, in view of that, the simulations in 2D and 3D may be very different and even cannot be used as a toy model. Moreover, in the case of our simulations of clouds, we obtained, without any ambipolar diffusion, efficient removal of the flux. And in terms of you mentioned the ideas of reconnection diffusion as a destruction of the flux through reconnection. I would not say that. It's reconnection facilitates the transfer of magnetic field flux in the turbulent media. So it works similar to the ambipolar diffusion. In general, I would like to know your opinion, how you think it is possible to combine the ideas, I think two proven ideas of ambipolar diffusion and reconnection diffusion for obtaining realistic simulations and theories.
Okay, all right, thanks. That's a lot of questions. I don't know if I can remember them all. So in our simulations, we have no numerical reconnection going on. Okay, so reconnection could certainly be happening, but on smaller scales than we can resolve. What we don't have is grid scale reconnection going on. Okay, now, I think some of the simulations that have claimed reconnection actually have grid scale reconnection going on, and the best they can do is claim, well, okay, this is representing something actually happening on another scale. Alternately, you'd need very, very strong turbulence, stronger than we have, to get field lines coming close enough to undergo reconnection in this simulation. Ultimately, your last question about combining ambipolar diffusion and reconnection, well, I think they really ultimately probably happening on different scales. They can both be happening, but I don't see how they're happening on the same scales.
I disagree, but they probably should.
Okay, all right, fair enough.
Any further questions for Shantanu? In the back there.
I think there's a misconception of the misalignment and magnetic braking efficiency because there's no actual reduction of magnetic braking when you have purely 90-degree tilt. It's just because there's lack of outflows, which you do not bring the angular momentum away from the circumstellar region. That's the main reason I think I demonstrated on 2013, and there's Masu Bates they demonstrated recently. It's just that is instead of braking.
Okay, well, fair enough. That may be, and at some level, the outflows, at least the jets, are driven by the twisted magnetic field, which is also the origin of magnetic braking. So I take your point. If you have no vertical component of the magnetic field, it'd be hard to generate an outflow. But I think the lever arm is another big part of it, the difference in the lever arm.
But even though you reduce the lever arm, there's in the unit of time, there's a much larger area that a fan wave can sweep around, so that at larger distances, you still have strong braking, even though it's perfectly 90-degree.
Right.
Okay, I think we'll have to bring this to a close. Thank you very much.
All right.